So this is just a fun video. A decade or two ago I was experimenting with individual defect motions, and the question arose, what would be the result of a systematic application of edge rotations to a small structure? So using the loose weave, I made the experiment, and it was quite elegant, and so I thought I'd repeat it for you. What we have here is an icosahedron added to the ground state. The bonding between the icosahedron and the ground state are 3 9-edge nodes. The 9-edge nodes have a curvature of +3, so altogether there's a +9 curvature. And then the icosahedron, which is normally 12 5-edge nodes, 3 of them are the 9s, so there are 9 5-edge nodes that remain. So that's a curvature of -9. So that's +9 -9 for this structure. So what I'll do is I'll rotate 3 of the edges that have connected to the 9 edge nodes together, and this will result in a general meshing out of the structure. It's sort of like taking a chocolate Easter egg and putting it on a hot sidewalk. I think you'll see. I've done just one of the 3 possible edge rotations. This rotation here, the edge had been here and now it's moved here, so this is a typical edge rotation. The effect is that these 9s are now 8s, and this 6 becomes a 7, but then one of the 5s becomes a 6, and so now it's +8 -8. I'll then do the 2 other edge rotations to complete this cycle. Now all 3 of the first edge rotations have been made. The structure looks like this. The ground state is actually fairly flat, and of course you can look into the inside of the what's left of the icosahedron. Of course, now there are 6 7-edge nodes around the periphery, and there are left only 6 of the 5-edge nodes. So now it's +6 -6. The next rotations are right here, where this 5 and 7, what in effect is a defect, will change this edge will change from here to here, and so the defect is moving out in this direction. I'll do this first for one and then for the other 2. I've colored one of the edges that I thought I wanted to rotate. This is connecting a 7 and a 6, and it would move as you rotate this edge. The 7 would become a 6, the 6 would become a 5, the 5 would become a 6, and the 7 would become an 8. And it turned out that this is the wrong edge to rotate. I've forgotten, because this would be making a 7-edge node an 8-edge node, and in general you don't want to do that. You want to always go to a lower curvature, as we've seen before. So I'll change the edge that I'm going to rotate. Now I've colored a different edge in purple. So this edge connects 2 7s, and if we rotate it like this, then this will become a 7, this will become a 7, and these 2 will become 6s. And that looks just like the right edge to rotate. I'll try that and we'll see what happens. I've rotated the purple edge now. It had been 7 7 6 6, and now it's 7 7 6 6. It's just shifted the curvature in a neutral fashion. So this looks like the right way to make this next series of edge rotations. So I'll do the other 2 now. I've done the other 2 rotations for the second cycle, and the structure is not very happy. There's a curvature here that's strained that indicates you know, the structure is syntactically correct, but it's stressed in some sense. But it seems to be the only way. So I found an edge here that I've colored in purple between a 7 and there's a defect here, 7 and 5. And if I rotate this edge, this will make this a 6, and this is 6, and this is 7, and this a 5. And that looks like that might work. I'll see. Again, this is turning out to be more curious than I imagined. I've made the 3 edge rotations for the third cycle. The structure is still relatively unhappy. You see there's a curvature over here in this, there's a 7 and a 7 and a 6 and a 5, and that just doesn't seem happy. And it's all in 3 places, over here and over here. So you notice the way I'm holding the structure now, you see how much distortion in the ground state there is in this when the structure is in this state. So this is an indication probably about the probability of this event happening. It's something I just didn't notice a decade or so ago, but I'll pursue it now. I mean, there's a defect here that I can move, and that will move this defect off in this channel, and the structure might get a bit happier at that point. I'll do all 3 of those. But you see, there really is this distortion in the ground state. It's just not happy is the way to think of it. So my sense at this point is that, you know, the probability of, if we go in reverse time where the edge rotations are coming together like this is improbable in some sense. So I'm learning something about the nature of the dynamics of this sort of structure just as I'm doing it, which is interesting. I've made the 3 edge rotations for the 4th cycle, and now I've colored the defects that result in purple. So there are 3 defects there that are, there's still there's a 7 and a 5, and there's another 7 over here. So either this defect or this defect could move. That is, this defect would go this way, and this defect would go this way. So which one happens, of course, is indeterminate. I think I'll take these 3 that I've put in purple, and they're free now, and so I'll just run them off in the next demonstration as if they're totally independent. But you notice how much distortion there is in the ground state. It's really very real. It's palpable. So that really says something. That's really very interesting. So you remember that there were 3 defects in purple in the last section. Well, they went steaming off in their relative directions, and they've left the arena here. So now, of course, you see that the ground state is pretty free of stress. So it's happy now. It wasn't earlier. Unfortunately, there's no defect pattern that we can use, because the 7 here and the closest 5 is here, and so you can't make a defect out of that for motion. So this lump of structure is anchored in the ground state. Now, how it got here is in effect an archaeological question, and because it can't move by itself anymore. We also noticed, remember at the very beginning of this video, that the icosahedron was also in a relatively flat ground state. So those are 2 terminal states of structure in some sense. and everything in between that I was complaining about being unhappy is simply unhappy, transient. So this is very interesting, and I guess this is the same conclusion I came to when I first tried this experiment. That is to say, I remember a lump of structure was stuck in the middle of, at the time I didn't build the ground state because I just didn't understand the ground state at that time. Now I have a relatively large ground state surrounding this structure, and so it's clear that the ground state is, well, more or less unstressed. So I've actually learned something from this process. It turned out that the video was not as much fun as I thought, but I did learn something, and that's the important thing. Well, one of the things that we see here is that this is a very symmetric structure. And you notice perhaps that I always did as many of the defect motions as needed to be done, but did them all in parallel. If we're talking about a real simulation, well then, where the signals are moving through the ground state in various ways, and there are many different signals interacting with each other, then events happen in a much more asynchronous and random and haphazard fashion. And so one wonders how one could accomplish even what we saw right here at all. I mean, so that's one of the goals for the future for simulation, to be able to obtain systematic and organized change by means of the signals flowing in the triangular neighborhood networks.